Welcome back, students. For the last couple of days, we have been studying the chapter Force and Laws of Motion. We have already studied about force, what is force, what are balanced and unbalanced forces, what are the possible effects of forces. We have already studied about Newton's first two laws of motion. In fact, Newton's laws of motion are the three physical laws that together laid the foundation for classical mechanics. They describe the relationship between a body and the forces acting upon it and its motion in response to those forces. More precisely, the first law defines the force qualitatively. As we had seen that from the first law, we were able to get an understanding about what is force. It gives us the definition for force. What about the second law? The second law offers a quantitative measure of the force. Now, if you remember in our previous class, using second law of motion, we had obtained an expression for force, F equal to m into a. M is mass and a is acceleration. So, obviously, using this formula, we can estimate the magnitude of force, and hence we got the standard unit of force, that is Newton. So finally, about the third law of motion, which is going to be the topic of study for today. This law asserts that a single isolated force doesn't exist. Now, before discussing what is third law of motion, I would like to tell you that these three laws of motion were first compiled by Sir Isaac Newton in his Philosophiae Naturalis Principia Mathematica, that is Mathematical Principles of Natural Philosophy, which was first published in 1687. Newton used them to explain and investigate the motion of many physical objects and systems. In fact, Newton showed that these laws of motion combined with his law of universal gravitation explained Kepler's laws of planetary motion. Now, before getting into Newton's third law of motion, let me quickly give a solution to the question that I asked in my previous class, that is, Newton's second law is the real law of motion. How to prove this statement? But prior to that, we have to understand what this statement actually emphasizes on. The second law states that the rate of change of momentum of a body is directly proportional to the force applied, and this change in momentum takes place in the direction of the applied force. In fact, using this law, we will try to obtain the first law of motion. Using the second law, we had obtained an expression for force, that is F equal to m into a. M is mass and a is acceleration. Now let us consider a situation when the external force acting on a system is 0. External force acting on a system is 0. What will happen if force is equal to 0? Using the expression for force, we can write down mass into acceleration equal to 0. Now just check both these terms. You are having a product of two terms, mass and acceleration. Out of these two terms, the first term, mass, is a constant quantity. What is mass? The amount of matter contained in a body. Can it be 0? Obviously not. Mass can never be 0. So, in this product, if mass is not equal to 0, then obviously acceleration will be equal to 0. So, since mass is not equal to 0, we get acceleration equal to 0. Hopefully, you remember the expression for acceleration. What is the formula for acceleration? A is equal to V minus U by T. And as per this result, we get this equal to 0. Obviously, if you take t to the other side of the expression, you get V minus U equal to 0 into t, then that will be 0. So now taking u to the other side of the equation, you get V equal to u. So now, what does this result help us to understand? Actually, this result tells us that there is no change in the state of the object. I repeat, there is no change in the state of the object when the external force is 0. Or in other words, we can say that in the absence of any external unbalanced force, there is no change in the state of the object. The object will either continue in the state of rest or uniform motion in a straight line. Now, this is actually the statement of the first law of motion, isn't it? The first law actually conveys the same idea. It tells us that an object continues in the state of rest or uniform motion in a straight line in the absence of an external unbalanced force. So just see the result. When f is equal to 0, v is equal to u. This means final velocity is equal to initial velocity. This means if initially the object was at rest, finally also it will be in the state of rest. If initially the object was in motion, finally too the object will continue moving with the same velocity in the same direction. This is the first law of motion. So we have been able to get the first law beginning with the second law of motion. That's why we can say that Newton's second law is the real law of motion. So now we will get into the topic of discussion for today, that is third law of motion. Before I get into the statement, let me ask a very simple question. Have you heard about this famous English proverb? As you sow, so shall you reap. Hopefully, all of you have heard this statement. This statement actually tells us that our actions, the way we behave, the way we talk, the way we act, all these have the repercussions on us. The way we behave with people, we will be treated exactly in the same way by others. If we do good to others, we will get back good in return. If we tend to harm people, we will exactly be treated in a similar way by others. So it is always advised that we should be nice and good to people. Physics also reaffirms this belief. Through Newton's third law, the same ideology has been communicated. To every action, there is an equal and opposite reaction. Action and reaction act on different objects. If we think of an interaction between two objects, like whenever we talk of force, force is obviously an interaction between two objects. So whenever two objects are interacting with one another, if one object is applying force on the other applies an equal force on the first. So the third law states that all forces between two objects exist in equal magnitude and opposite direction. If one object A exerts a force F1 on the second object B, then B simultaneously exerts a force F2 on A, and the two forces are equal in magnitude and opposite in direction. So how can we represent this situation? If object A applies a force Fa on object B, then object B also applies a force Fb on object A. These two are equal in magnitude and opposite in direction. So the equal to sign is for equality in magnitude, while the negative sign is due to the direction. We all know that force is a vector quantity, so we have to take care of the direction. So these two forces are equal in magnitude but opposite in direction. The third law means that all forces are interactions between different bodies or different regions within one body, and thus there is no such thing as a force that is not accompanied by an equal and opposite force. So it is just not possible that we can imagine that an isolated force is existing. Forces will always exist in pairs. One force is called action, while the other force is called reaction. This is due to the same reason that Newton's third law is sometimes referred to as the action-reaction law. The other part of the law also gives a very important information that action and reaction act on different objects. Like in this case, we are having two objects A and B. So if action is acting on B, reaction is acting on A. So it should never be believed or understood that being equal and opposite, these two forces will cancel out or rather balance out. No. Balanced forces can exist only when all the forces are acting on the same object. When a number of forces are acting on the same object and the net force is equal to 0, then we say that the forces are balanced. But in this case, action is acting on one object while the reaction is acting on the other object. Like if we are hitting the surface of a table, then the force that we apply on the table is action, while the reaction force is going to act on our hands. So that's why we get hurt. So the reaction is acting on our hands, action was acting on the table. So the two forces, even though they are equal, but they cannot be added and then equated to 0. They cannot balance each other because these two forces are acting on two different objects. One force was acting on the table, the other force was acting on our hand. So action and reaction act on different objects, and at this very case I will mention an important thing, that action and reaction forces never balance each other. Action and reaction forces will never balance each other. This you need to remember. There are many examples in our day-to-day life that can be understood with the help of Newton's third law. You will be surprised to know that Newton's third law can be used to analyze some common daily activities, and these further find an application in such big industries. So let's see what are the different fields in which Newton's third law finds its application. Some of these have been shown on the screen. You can see from the simplest activity of walking on the ground to coming out of a boat to aeroplanes, rockets, recoiling of gun, all these are based upon Newton's third law of motion. We will analyze a couple of these situations one by one. Let's begin with the simplest amongst them, walking on the ground. Newton's third law states that every action has an equal and opposite reaction. This is relevant to walking because when you put your foot on the ground, you are applying a force to it. In doing this, the ground also actually applies an equal force onto your foot in the opposite direction, pushing you forward. Now, in order to understand this situation, let me show you the picture. Let me zoom it a little bit. You can see that when we are applying force on the ground, there are two forces. The force has been distributed in two directions. Force on road by you, as we are applying the force by pushing it backward, and obviously the weight is acting vertically downward. The resultant of these forces is shown in the diagram as net force by u. Now this is action. The reaction force is going to be applied by the road. So you can see there is a normal force that is acting vertically upward, and along the surface of the road there is force of the road on u. So the resultant of these two forces is written net reaction force, and this net reaction force is actually helping us to walk on the ground. So in this way, Newton's third law can be used to understand how we are able to walk on the surface of road. Movement of balloons. A very common observation, but put to such an important use in a big industry. Let us analyze this situation and figure out where actually this ideology has been put to use. You might have seen that when air rushes out of a balloon, then it starts moving in the forward direction. Or if you are holding a balloon in your hand and air starts coming out of it, the balloon will start moving upward. Why does it happen? When we let go of the end, the air rushes out and pushes against the air around the balloon to move it in the opposite direction. As you can see in the picture, when the air is rushing downwards with a force that we can refer to as action, this action will create an equal and opposite reaction. Now this reaction force will be acting on the balloon. And since the action was acting in the downward direction, as the air was going downwards, the reaction force will be applied in the upward direction. And this reaction force will help the balloon to rise upward. So that's why you find that when air comes out of a balloon, it starts moving upward. Now the question arises, where does this idea find its use? This idea actually finds its use in the movement of rockets and jet aeroplanes. Inside a rocket, there is a fuel chamber. When the fuel burns, hot gases are ejected from its rear end, as you can see in the picture, exhaust flow pushed backward. So the hot gases come out from the rear end of the rocket. This is action, and this is going to create an equal and opposite reaction. So you might have seen when a rocket is rising upward, such a tremendous amount of hot gases are ejected from its rear end. And these gases actually provide the reaction force to the rocket that helps it to move upward. Similarly, in the case of jet aeroplanes, the hot gases that are ejected from the rear end of the jet that goes in the backward direction gives a forward thrust to the jet aeroplane. So a simple observation made in the case of balloons finds a similar use in case of rockets or jet aeroplanes. You might have seen that whenever we jump out of a boat, whenever we come out of the boat tends to move in the backward direction in the water. So that's why it is very necessary to tie the rope with the help of a rope to the plank so that this possibility of the boat getting drifted away in the water is prevented. So as the man jumps off the boat, he exerts the force on the boat and the boat exerts the reaction force on the man. So obviously this reaction force is helping the man to jump out of the boat. But the force that is applied by the man on the surface of the boat is responsible for making the boat move away on the surface of water. So the man leaps forward onto the pier while the boat moves away from the pier. So it is important to tie the rope with the help of a strong rope with the pier so that this possibility of the boat moving away on the water is prevented. Why is it difficult to hold a hose pipe in its position? Now, do you all know what is a hose pipe? It is a pipe having a broad opening through which huge amount of water comes out. You might have seen firemen carrying these sort of pipes to put off fire, because in case of such kind of an incident, huge amount of water is required to put the fire off, and for that they make use of a hose pipe. Now it is extremely difficult for the fireman to hold the hose pipe in its position. As you can see in the picture, the forces acting into opposite direction, action and reaction. What is action in this case? The force with which the water is ejected. And what is reaction? The force applied by this water on the hose pipe. So as the water is being ejected with a tremendous force, large amount of water is ejected from the hose at a high velocity. So as per Newton's third law, water pushes the hose in backward direction with the same force. So therefore it is difficult for a fireman to hold a hose in which it ejects large amount of water at a high velocity. You can see in case of an aeroplane and any aircraft, how Newton's third law finds its application. So in the different parts of this plane, you can see in which direction the forces are acting. So what is action and what is reaction? In one part, in the wings, you can see the action is air deflected downward by the wing. Well, what is reaction? The wing deflected upwards. The upward lift. Then air pushed and pulled backward by the propellers, that is action. Reaction, propellers pushed forward. So in this manner, in aerodynamics too, you find an important application of Newton's third law. Why does a gun recoil? Whenever a person tries to hit a target using a gun or a rifle, they feel a jerk on their shoulders. Now, if they are using a rifle, this jerk is a tremendous one that may even hurt their shoulders. So, always they are given proper training before they start practicing with the heavy gun or a heavy rifle. so as to avoid the possibility of getting hurt in their shoulders. But the question arises, why does the gun give this jerk on the shoulders? Why does the gun recoil? The term recoiling is actually used to refer to the backward movement of the gun whenever a bullet is fired from it. Now, how we can analyze this situation? We can analyze this situation using Newton's third law. When the bullet is fired from the gun, it comes out with a huge force. It experiences a force in the forward direction. Now, obviously, if there is action, there should be an opposite reaction. So, this reaction force is acting on the gun, due to which it is pushed backward. Even though the mass of the gun and the mass of the bullet are not equal, the bullet is extremely light as compared to the mass of the gun. So, the distance through which the gun moves backward is hugely less, smaller as compared to the distance moved by the bullet. But still, a backward thrust, a backward jerk is experienced whenever a bullet is fired from the gun. Now, this situation is referred to as a recoiling of gun that can be understood with the help of Newton's third law. Now, finally, coming to a very important situation that is often asked in the examinations, that is the horse and cart problem. How does a horse pull a cart? As you can see in the picture, the horse is tied to the cart. So, if the horse wants to pull the cart and applies a force in the forward direction, since it is tied to the cart will obviously pull the horse backward. So, then how the horse can make the cart move from its position? In this case, the horse and cart make one single system because they are tied to one another. So, whatever effort is applied by the horse in making the cart move in the forward direction, an equal force is applied by the cart in pulling the horse in the backward direction. So, in order to make the cart move, the horse has to push the ground in the backward direction. By pushing the ground in the backward direction, the horse tries to make the cart move in the forward direction. Now, one thing that has to be understood in this situation, if the effort applied by the horse in pushing the ground is able to overcome the friction, you can see the force of friction labeled here. So, if the force applied by the horse on the ground is able to overcome the friction force between the cart and the ground, then the cart is going to move. So, if the horse keeps on pulling the cart, then the cart is not going to move. In order to make the cart move, the horse has to push the ground backward. And the reaction force that is applied by the horse, if the reaction force applied by the ground on the horse is more than the friction existing between the ground and the cart, then the cart is going to move. So, these were a couple of situations related to Newton's third law. Newton used the third law to derive the law of conservation of momentum. However, conservation of momentum is a more fundamental idea, but still, you will be able to derive this law using third law, and this law will hold in cases when Newton's third law appears to fail. So, now that we have understood all the three laws of motion, we can see that the analysis of so many commonly observed situations becomes so easier when we have a deep understanding of these three laws, first, second and the third law. So I will suggest you to go through more examples, common examples that you can relate to your day-to-day life, and see if you are able to analyze it using Newton's laws. Thank you.